Let us now do for your degree of freedom, which is the 6th degree of freedom. Go back to the plan again. This was the original problem, this is the plan. I redraw the plan again. So, there are column corners, what we have here the columns. These columns are numbered in the same manner as we have here 1, 2, 3, 4 same style. Let us say 1, 2, 3 and 4. Let us say I am also going to mark the centroidal axis of this. Okay. Now, I am going to give rotation about the z axis. Okay. That is yaw. So, let me draw the new position. Let me give the rotation. Let me draw the new position. Okay. We call this angle as theta 6. Let us, okay, this is going to be 1, 2, 3 and 4. I have rotated clockwise. Let me call this dimension from here as A and from here this dimension as B. In simple terms, B offset with A offset will give me my rotation. Okay. These legs will undergo new tension, which will be T0 plus delta T6. This leg will also now undergo a new tension, which will be T0 plus delta T6, and similarly all of them. Okay. That is how the rotation happens. So, now the cable length will increase by a small amount, which I call as L1, which will be L square plus theta 6 square of A square plus B square the whole root, with reference to this figure. Okay. I call this as equation number. So, change in pretension in each leg is given by delta T6, because the rotation is about 6 degree, which will be L1 minus L of AE by L, that is in each leg. Okay. Equation number. Force in heave direction due to this rotation will be K36 into theta 6, which will be L by L1 minus 1 of T0 of 4 legs plus L by L1 of delta T6 of 4 times, which gives me K36 as 4 T0 by theta 6 of L by root of L square plus theta 6 square of A square plus B square minus 1 plus 4 delta T6 by theta 6 of L by square root of L square plus theta square A square plus B square. I call this equation number 12 and 13. K66 will be now equal to T0 plus delta T6 of A square plus B square by L1 of 4 times, which in simple terms 4 times of T0 plus delta T6 A square plus B square by root of L square plus theta 6 square of A square plus B square. I call this equation number. So, friends, let us now assemble the stiffness matrix. Let us say the stiffness matrix derived from first principles is like this, which is K11 0, K31 0, K51 and 0, 0, K22, K32, K42 and 0, all values of 0 except K33 in heave. Similarly, in roll we have K34 and K44, remaining all are 0. In pitch we have K35 and K55, remaining all are 0. In yaw we have K36 and K66, remaining all are 0. So, that is my 6 by 6 stiffness matrix for TLP. One can very easily see some important observations on this for our understanding. What are the observations we can see from the stiffness matrix? First and foremost, you see heave coefficients are present in all. It means you give unit displacement in surge, sway, heave, roll, pitch and yaw, you get forces in heave direction in all the case. It means heave is strongly coupled with all degrees of freedom. You take a box which is floating, okay, give a heave displacement, it will influence surge, influence sway, everything. Okay. So, heave has got a strong coupling. The second observation what we have is stiffness matrix is square and non-symmetric. K36 is present, but K63 is not present. For example, K35 is present, K53 is not present. So, stiffness matrix is square, but non-symmetric. So, it also says that presence of off diagonal terms reflect coupling between degrees of freedom. Take for example, any one specific coefficient, let us say K66. So, the coefficients of stiffness matrix depends on tether tension variation and change in tether tension variation, you see here. So, I should say that K matrix is response dependent because T0 changes only when there is a displacement. Number 1, change in T0 Kij is response dependent, change in T0 results in alternate tension and compression, which results in fatigue, failure of tethers. So, friends, interestingly, in this lecture we have learnt how to derive the stiffness matrix from first principles. So, one can give a very clear summary. The stiffness matrix of TLP is not constant at all times. Coefficients change with time step which depends on T0 and xi. Let us see what would be my mass matrix. If this is my mass matrix, which is again going to be a square matrix, I should say M1 0 0 0, this is also going to be 0 and 0. Similarly, M2 0, all zeros. Similarly, all zeros with M3, then all zeros with M4 or M22, M33, M44, and all zeros with M55 and all zeros with M66. This is the ideal mass matrix, but some added mass will be added to this. Let us quickly see what is my M11, M22 and M33. This will be equal to the mass of the platform. M44 will be the mass of the platform into Rx square. M55 will be mass of the platform into Ry square, and M66 will be mass of the platform into Rz square, where Rx, Ry and Rz are respective radius of gyration about x, y and z axis respectively. Now, what would be the added mass term? The added mass matrix will be interestingly MA11 0 0 0, MA51 and 0. Similarly, nothing added in the second column, but in the third column there will be MA33. In the fourth column nothing added, there will be MA33 and MA53. Fourth column, then fifth column and sixth column. So, what is going to be MA11? MA11 is going to be pi dc square by 4, that is the diameter of the column, into Cm minus 1 rho w of x dot surge. Then what is going to be MA33, which is going to be pi dc square by 4 into rho w into Cm minus 1 of x double dot heave. Then what is MA51 and MA53? MA51 is added mass moment of inertia due to force in surge degree. Similarly, MA53, as you correctly guessed, is added mass moment of inertia due to force in heave degree. So, this is added mass moment of inertia in pitch degree due to force in surge degree. Similarly, the added mass moment of inertia in pitch degree due to force in heave degree, that is why it is MA53. Okay. Now, we have K matrix derived, M matrix derived. I want to use the computer program to find C matrix and then f of t and then solve the problem by Newmark's iteration scheme, which we already gave you in the last lecture. Here typical TLP, very interesting data, will have weight in kilonewtons as 209,500, buoyancy force in kilonewton as 334,000, T0 in kilonewton will be 124,500 for a length of 471 meters for a water depth of 500 meters. The H bar is generally seen as about 26 meters for this platform. The size of the platform is 92.5 meter by 92.5 meters. Diameter of the column and diameter of the pontoon members are about 14.2 meters. Rx and Ry are 29.15 meter and Rz is 32.10 meter, and the axial stiffness in cables is about 58060 kilonewton per meter. This is a typical example TLP based on which I want you to find out the mass matrix, the K matrix, run the software or run the coding which I gave you in the previous lectures. You will find that the period of surge and sway will be about 83.33 seconds and period of heave will be about 1.92 seconds and period of pitch and roll will be about 1.9 seconds and period of yaw will be about 75.2 seconds. So, please verify these results using the program of Eigensolver which we gave you in the last lecture. So, this lecture summarizes how to estimate the stiffness matrix, the mass matrix and of course, the damping matrix for a typical TLP as you see on the screen now. Thank you very much.